1 hour is enough.
Okay. Can I start?
Pronounce your name for me.
Whole name or just Guilherme?
Guilherme.
Yes, Delfino.
Delfino.
Yes, or you can just say Gui Delfino. It's fine. Sorry?
Português.
Yes. Oh, você é o português da brasileiro. Sim. Qual é o seu nome? Your name?
Bruno.
Bruno. Prazer.
Muito prazer.
Yeah, Juven mentioned there was the Portuguese person. I thought it was Francisco Machado.
Sou José, bom dia. Bom dia.
Bom dia.
Bom dia.
Yeah.
Yes.
It's like good morning.
Bom dia.
You can say boa tarde.
Okay, welcome everyone. We are very happy to have Guilherme Delfino from Boston University, and he'll be speaking about modular gauge series and the fractal behavior in 2 dimensions. You should, interact with Guy and ask questions and just relax.
Perfect.
Feel free to interact.
Okay.
Let's welcome Guy.
Thank you very much for inviting me, Juven, and thank you all for attending this unusual time, unusual day kind of seminar just before Thanksgiving. So I'm more than glad to present about this 2 pieces of works that I've developed with my advisor, Claudio Chaman at PU, and Professor EGU from Northeastern. And this talk's kind of a summary of some lessons that we learned along the way. And please feel free to interrupt me at any time. Also, I'm assuming that people on Zoom, they can hear me. I'll just proceed. Yeah, so just to put some context, one of the main goals, right, in condensed matter theory is the whole, have a big table with all the phases of matter, and then we understand very deeply whatever happened in each slot of this table. And symmetries, they have proven themselves to be very good tools for that. So from Landau and from recent developments and SPTs, we learned that usual symmetry groups G, they give us a very nice approach to talk about this classical phase of matter and SPTs protected by these symmetry groups. And even more recently, a lot of exotic and richer phases of matter where they were also put in this language of symmetries with these generalized notions of symmetries, like higher form symmetries, subsystem symmetries, and so on and so forth. I didn't even try to put references here because every day on arXiv, it comes out some 2 or 3 papers on the topic. So it's a very hot topic right now. And the things that I want to tell you today a little bit, they also kind of fit in this framework of a generalized notion of symmetries. And they're associated to these things that we call spatially modulated symmetries. So the idea is the following. Whenever we have a global symmetry, like a continuous symmetry, we have a generator for it. And this generator can be, usually it is expressed as a sum or an integral over some charge density. So if you don't have this function here in the middle, this f of r, so this is just global symmetry, and you can think that this generates, I don't know, a U1 symmetry. However, we want to generalize this notion of a generator and allow the possibility of having this function here. So that's why we have this name, spatially modulated symmetries. So it's a symmetry generator that is modulated along our lattice or along our space. And an immediate consequence of this is that now this generator does not commute with translation transformations anymore, because now since the generators depend explicitly on the position, this does not hold. So now our symmetry is not an internal symmetry anymore. It's like a mixture of internal symmetry and crystalline symmetry. And we are going to see a lot of examples of this.
Just make sure. So is a rho of some kind of density?
It's some kind of density of charge, yes. I'll tell you later what precisely this rho bar is.
It's a form of the f of r.
So the f of r, in principle, we can choose. So along this seminar, we'll be exploring different f of r's and what they tell us about the low energy physics of our gauge theories. Yes.
Is f of r required to be somehow periodic?
It has to be consistent with your lattice. So if you want to impose periodic boundary conditions, then you want to impose this function to also have the same periodicity of the lattice. And you also want to make sure that this thing doesn't diverge and is well defined. We are going to discuss that as well.
So this form possibly contain previously the other type of the subsystem symmetry.
Yes.
This will be a generalized form.
Yes. We can think that subsystem symmetries, they kind of are special cases of this, when this function is like very sharply concentrated in some region, like on a plane, for example.
And you will give more details.
Yeah. I'll also talk a little bit more about this. Very good. Keep the questions coming. And one of the main ideas, one of the main motivations to study this kind of symmetry generators is because they can naturally constrain dynamics of excitations. As a historical proof of this is that Michael Pretko, back in 2017, he had this idea of choosing this function to be degree 1 polynomials in the coordinates x, y, z for coordinate r, and then gauging the symmetry to get some kind of effective field theory, like some rank 2 symmetric tensor field theory as a description for gapless fractals. And the intuition that these symmetries, they impose constraints on the dynamics of excitations is that now, if we want to move excitations apart, they have to be moved such that all the symmetries, this thing is still constant. This thing is conserved. And in this talk, we are basically exploring this kind of philosophy, but for Zn, not continuous groups, but Zn, and everything is going to be defined on the lattice. Yes. Oh. Sorry. Yeah. So the plan for the talk is I'm going to tell you a little bit about what fractons are, and after this, I will try to make more precise what I call this modulated gauge theories here and how they correspond to topological order on a lattice. And after this, we are going to explore some specific functions there. We're going to fix some function and then study the low energy physics and discuss how they are connected to two-dimensional fractonic physics. Yes. So first, let me tell you what a fractonic system is. So if you read in the literature, a lot of people call different things fractons. And this is like a list of properties that we see in fracton systems. But sometimes we see some property in some system, but not other property, but people still call those fractons. So I think because the field is so recent, there is no like strict definition that everyone agrees what fractons are. But these are like properties that all the models that we all agree to call fractons, they share. And they go something like this. First, if we want to talk about this topological fracton order, we are always talking about these gapped topologically ordered systems. And when you read this, you should have in mind that here on this fractonic kind of systems, we have all the funny things that usually happen on topological order. So we have fractionalization of statistics, we have fractionalization of charge, and so on and so forth. The phase is very robust against perturbations and etc. But on top of that, these fractonic systems, they also present this special property of restriction on mobility of quasi-particles. So you have your vacuum, you create some excitations on the top of the vacuum, localized on space, but now this excitation cannot move from this point. And this is interesting for a lot of reasons. This gives rise to Hilbert space fragmentation, slow thermalization. This, in principle, could give us a better platform for finite temperature quantum memories and a lot of motivations, and a lot of people from different communities studying fractons for these reasons. And this gives us this idea that on top of fractionalized charge and fractionalized statistics, the anyons here, they also present this kind of fractional mobility. Yes. So most of these fractonic systems, they are associated to these generalized notions of symmetries, either subsystem or modulated symmetries. And we're going to focus mostly on the second. And I'm going to argue that the first is just a special case of the second. And finally, but not least, we have this kind of phenomenon of UVIR mixing of scales. So something that is observable in the IR, for example, ground state physics, ground state degeneracy. There's nothing more IR than ground state. It depends on the UV details of the system as how many sites you have in your lattice. Yes.
So simple things. Just make sure when you say n-dimensional particle, you really mean zero-dimensional particle restrict to move in n dimension, right?
Perfect. Yes, I skipped this bit. But these particles, they are all point particles, and we call them subdimensional particles. And the dimension of this subdimensional particle is associated to the submanifolds that they can move. So if you have a three-dimensional system, you have a point particle here. Maybe sometimes this particle cannot move at all. So I call this a zero-dimensional particle. But sometimes this particle can move along straight lines. And then we call those one-dimensional particles. Or sometimes this particle can move only along planes. And then we call these two-dimensional particles. And then I have these funny names for them.
Okay. Yeah.
Is there any relation between the subsystem symmetry and the icon symmetry?
There are some relations. Like some people think that subsystem symmetries are higher form symmetries that are constrained to be topological only along submanifolds. So I would say that the subsystem symmetry is the geometric analog of the topological properties of higher form symmetries. So in higher form symmetries, you usually can deform your objects as you wish. But now in subsystem symmetries, you can deform them, but only restricted to some submanifold. Could be a line, or could be a plane, or etc.
Will you elaborate that relation between subsystem and higher symmetry?
No. I'm just saying.
All that with modulated symmetry?
The modulated symmetry, since they are very rigid on the lattice geometry, I can only relate to the subsystem, but not with the higher form. Higher form, they are too topological for me.
Few more questions. What do you mean by fractional mobility?
Oh, this is just something that Vijay and Ha, they put in their paper to argue for the name of fractons. So fractons, they have this name because they kind of have a fractionalized mobility in some sense. It's just like, as a pair, for example, in the toric code, you have a pair of anyons. This is a local boson, right? So two anyons is a local boson. But then we think that this boson fractionalize into two, they split into two. And now each one of these quasi-particles, they are something per se, they are anyons. And this is kind of the same. So we can create a bunch of fractons together. This bunch of fractons that we create, they can move. But as you separate them, now they lose their property of moving. So by themselves, they cannot move. Yeah, that's the story.
That also helps to audience to follow what you mean.
No, yeah.
Let me also ask, are there literature consider maybe some restriction of the, let's say, p-dimensional objects instead of a zero-dimensional particle? The p-dimension, p can be 0, 1, 2, 3. restrict to n-dimensional submanifold, that type of restrict the excitations. Here you only consider 0 dimension restricting n-dimension submanifold.
Yes.
The p dimension. And then
Yes, I would say that maybe the paper from David Essen, they have this very general construction for Fracton phases. I'm going to show this paper later, but there they construct topological phases as gluing together n-dimensional topological orders. And then there you also have the possibility of having, instead of just strings, you could have one-dimensional line defects or membrane defects and so on and so forth. Yep.
Are there something particularly surprising? You are saying more like a spectral topological order. That sounds not surprising.
Yeah. I don't know. Maybe. I don't know. Good question. Yes. And just to motivate why we're talking about fractons in 2 dimensions is because 2 dimensions appear to be very funny for the fracton business. So first, we note that in 3 dimensions, that are the models that all the people believe that they have found their fractons, we usually have this kind of property. As you count how many ground states you have on a periodic manifold, like a periodic lattice, the ground state degeneracy, how many ground states you have, actually depends on the system size. So L, if you have a 3-dimensional system, L by L by L, this is just the linear size. And this is what I meant before by UV-IR mixing. So depending on how you regularize your system, this changes completely the low energy physics. And then this led Ha back in 2021 to prove this theorem, assuming very, very mild assumptions. So if he's just assumed that you have a homogeneous topological order, and he managed to prove that in D dimensions, so this D here are spatial dimensions, in D dimensions, the log of the ground state degeneracy cannot scale better with the linear system size as D to the power of 2. D as to the power of D minus 2. This C and this mu here are just constants that depend on the topology of your lattice and on your local Hilbert space dimension and do not scale with L. And this D minus 2 immediately led us to think what happens in D equals 2. So in D equals 3, this is just linear in L. This just recovers what we already had before. But now, what about D equals 2? Does this imply that we cannot have fractons in D equals 2? That's a question to bear in mind. And also, another papers, for example, this one that I mentioned before from David Essen and people and collaborators, they actually conjecture that fracton phases should not exist in 2 dimensions. So they have this way of building fracton phases from this network of topological defects. And if their conjecture is correct, then we cannot have fractons in D equals 2. So here, from now on, we want to explore this idea of how fractonic a 2-dimensional system can be. Like maybe it cannot be cannot present all the fracton properties. For example, this property definitely cannot present. But what else can we have?
Space dimension.
Space dimension, yes. So here we should always be thinking that we are working on a lattice. So we have like a Hamiltonian, and D is just the dimension of this lattice.
So is this behavior a lot of a ground state degeneracy as a large L behavior here?
It's like a large L behavior, yes.
And into although the constraint by equation 3, their constraint is GSD should bounded by some constant.
Sorry, say that again.
I say that when the spatial dimension is 2, space dimension is 2, the equation 3 say the local GSD.
Oh yes, perfect.
By some constant.
Bounded by some constant that does not scale with L.
Yeah, all the one constant, you're right. But
yeah.
Is there a possibility for this goes like logarithmic? So which means
no, it cannot grow. Well, yeah, like in D equals 2, you should think of this as you take L to infinity, the log of the ground state degeneracy should not scale with L at all. Should be upper bounded by some constant.
Yeah, from the equation, that's the way to say that. I mean, this equation say GSD will bounded by exponential some power L.
Yeah, this number can be large. This can be large. But when I say that is order 1, it's like order 1 and L. But depending, for example, what your degrees of freedom are, or depending on the
Sorry, order 1
in L.
Order 1 is just order 1.
Order 1
It's
is
independent of L.
not independent. It can depend on, well, I'm going to give you an explicit example, but it can depend on L. But what you should read from this is just as you take L very, very large, this thing is not very, very large. Yep.
So if I fix, so you said the constant C and mu depend on the topology and on the number of degrees of freedom at every site. So if I fix these properties, is there a universal bound on the ground state, a universal like upper bound on the ground state degeneracy into dimensions across all topological orders?
Yes, I would say so. Yes.
On our case, as dipole consideration, it's also in 2D. It's standard level, a complete example of the no-code for Fracton.
That's a very good point. For 2D, so usually you have this, if you just gauge dipolar symmetry, you're going to have some U1 rank 2 gauge theory, right? But then if you Higgs this, like we want to gap it topological order. If you Higgs the U1 down to Zn, now the ground state degeneracy is actually upper bounded. It does not scale with L. What happens in the dipolar 2D case is going to also happen in this very same model that I'm going to present later. We'll come back to this.
Actually, just make sure, what do you mean by order 1 there? You said it has L dependent, so what do you mean?
It's just like how it scales in asymptotically. As you take L large, this does not grow neither polynomially or exponentially. It doesn't grow at all with that. That's what I mean.
But this order 1 number is independent of L, right? Independent of L.
Like, for example, say if L is even, the ground state degeneracy is even, and if L is
Precisely. You can have some modulation.
Okay, you have L dependent value.
Exactly.
Okay.
Exactly.
Sorry.
Yes. But very good question. Yes. Yep.
But let me make sure. So is GSD can go like L? Is it possible? So you are presenting local GSD goes L, which means this goes exponentially. Okay.
Yes.
Goes like L.
Not in D equals 2.
Okay.
Maybe in D equals 3. Yep.
Maybe in D equals
Maybe in D equals 3, but not in D equals 2. Yes. So now we talk a little bit about this fracton. So let's see what we can get by these spatially modulated symmetries. So this expression is just the lattice version that I mentioned before. So this is just I replace the integral over the whole space by a sum over lattice points. So this R should be thought as summing over vertices. And in the back of your mind, you should always think that we're working on a square two-dimensional lattice. And here we have this f of R function that can assume values depending which position on the lattice you are. So we can consider some familiar cases just to have some explicit examples in mind. So if we just fix this function to be a constant, for example, 1 everywhere, this is the usual U1 charge conservation. So this is just a sum over some charge density, and then in the end we have the total charge, and this exponentiating this generator, we can define symmetry operators. If we allow this function to be degree 1 polynomials, like in x and y, this corresponds to dipole moment, and we can make this actually any kind of polynomial. Order degree 2 polynomial would lead us to quadrupole momenta conservation kind of thing. And in general, for nth order polynomial, nth degree polynomial, we have this 2 to the power of n kind of multiple conservation. So these are explicit examples to think. And once we have this generator, so what I'm saying is that I want to build, or I want to consider models, systems that are invariant, that preserve this kind of thing. So this generator is a conserved quantity. And now I can just exponentiate this generator and define some symmetry operators. So this alpha here, yes.
Sorry, the lattice extent and bound of the lattice polynomials.
Very good question.
So if that's periodic boundary.
So this is a very good question, because later, so to get rid of some problems with the U1, I will not require this G to be always conserved, strictly conserved, but be conserved only mod n. And then there is some consistency relations between the size of the system and this n of the group order. Precisely because of this. As we approach the boundary, this thing, as imposed periodic boundary conditions, this thing should be well defined. Very good question. Yes. And from now on, I'll be always talking about this bosonic degrees of freedom. So in the end, when I write down some kind of Hamiltonian, the degrees of freedom in my Hamiltonian, they're all bosonic. So we can already see what is the action of these symmetry operators on our bosonic degrees of freedom. So you could think that this B is just some destruction operator of a boson on site R. And as we conjugate with U and U dagger, what we get is like this phase here. So you can see that this is a straightforward generalization of our usual U1 shift symmetry, the phase shift symmetry. Yes. So as an explicit example, again, as this function is just one, just a constant, we can explicitly write down a Hamiltonian that conserves the total charge, and it is invariant under this phase shift, which is just B dagger. It's the usual two-body hopping terms. I destroy a boson at site R, and then I create it in the neighboring site. And in the following, I'm going to use this A here to schematically represent like these different directions that the particle can help. Yeah.
Just make sure. So it's very clear how the boson field transform under the exponential symmetry generator there. But is it clear how is there some periodic constraint? Maybe he was asking this, but is there a periodic constraint on the exponential by alpha f?
Perfect. Yes, very good question. So here I'm always talking about this U1 kind of symmetry, but in the end I don't want to talk about the U1 at all. This is just like an introduction, but I want these bosons to be conserved only mod n. So you should think that these bosons, they're like, I don't know, some sort of generalization, some sort of Zn bosons. And if you just take B to the power of n, this is the identity operator. Yeah, so I'm just introducing this matter Hamiltonian, but you're going to see that they are very, very complicated, and I don't want to deal with those. But I'm going to come back to your question when I formally introduce the Zn degrees of freedom.
So what's n here? The number?
So n is just integer number that you choose. So the idea is that we are going to break U1 down to its subgroup Zn, and then n is some parameter in the theory.
But it can be arbitrary, or is it constrained by some of the data you presented earlier?
So n is arbitrary, yeah. So you should think that n and the function kind of defines the theory. You fix n and you fix the function, and I tell you all the properties that you want to know.
But what's the problem for U1, which is so periodic? What do you say U1 has a problem again?
It's just because this well, it's because when the generator is strictly conserved, you have to be careful what the kind of functions that you impose here, such that this thing is well defined under periodic boundaries conditions. So for example, you should have that f of r, as you go around the system, should be equal to f of r plus lx, let's say. And this constrains a lot what kind of functions you can have. It's not any kind of function that you can have. You should have some periodic function. But I want to avoid that by saying that this thing is not strictly conserved, but only mod n. So this function, as I go around the system, f of r is equal to f of r plus lx, let's say, mod of n, only mod n.
So if it's a U1, all the charge associated with this polynomial expansion each symmetry is labeled by Z, I suppose, right?
Yes,
Z.
yes, yes.
So
yes,
once you
yes.
break down to Zn, but you want to break down Zn, then all the charge associated with each polynomial also becomes Zn.
Yes, yes.
But then you seem to suggest there's some trouble for U1, but you also say that I can take arbitrary Zn. So I was wondering why n has no constraint at all. Well, there's a constraint.
Well, I would say that Zn has avoided these problems that I'm mentioning, because any function that you put here, we only have one constraint over this function if we allow this to be a Zn theory, which is the function on every lattice site should be an integer. Yeah, so that's it. That's the only constraint that I have if this function is defined over Zn. If the function is defined over like the U1, if these are U1 bosons, now you have an extra constraint. You should say that this function here is actually periodic with, it has the same periodicity as your system size. This is a way stronger thing. For example, something that is periodic is a cosine. So you should put a function that is like a cosine of R. But now this cosine assumes non-integer values. So this is problematic. I want to avoid all of those problems. Yep.
Thanks.
Yep. Please keep the questions coming.
Do you only consider U1 symmetries? Like, can you have this modulated symmetries with other Lie groups?
Like non-abelian crazy
Yeah,
Lie groups?
I guess SU2 modulated symmetry.
Maybe. Maybe, yeah. I was thinking about the generalization of Zn to like some finite non-abelian group. I think it's possible. Yes.
Just also, then the modulated low symmetry. So if we consider charge density width, the charge density width is, let's say, even in the non-modulated low symmetry, it breaks the cancellation symmetry.
Mm-hmm.
But is that say that the charge density width becomes symmetric under this modulated low symmetry?
I think you can say so, yes. Yep. So this is like some emergent kind of symmetry, right, in your state. But here we are, I think the difference is that we are imposing this to be a symmetry in the whole Hilbert space. Yeah, in the whole, it's a symmetry of the Hamiltonian. Yeah, that's what I mean.
We'll just make sure also that equation A, this Hamiltonian, is that not necessarily conserve the solution we just wrote right now? These are just some of the leading orders have sent, or does it is conserved?
These are like leading order, yes. We could have like 3 dots here, but in the back of your mind, you should think that anything that you add here, like interaction terms, they should also respect the U alpha symmetry operator.
But the equation A alone without does it conserve? Does it preserve the symmetry?
Yes.
It does.
Yes.
But there's a hopping on different sides, and so there's some constraint between the exponentials.
Yeah, because for this explicit example, so this is an explicit example where the function is a constant.
Okay.
So when the function is a constant, this is just the usual phase shift.
This is fine. I'm saying more general F.
Oh no, yeah. So for more general F, things are more complicated. So for more general F, we have this generalized hopping term here that is schematically I'm writing like this, but the form of it actually depends what the function is. Yeah, so the idea is, again, we want to write some leading order term, Hamiltonian, in terms of these bosonic degrees of freedom, that conserve this G of F for arbitrary Fs. It's very hard to do. We cannot do this in arbitrary cases, but from now on, I'm just going to write this schematically like this, and I can provide some examples. Just one comment before that. These deltas here, this delta IA or AR, they should be thought as integer coefficients. that define this kind of lattice derivative operator here. So every time that I have this kind of sum over AR, I'm going to call this a lattice derivative operator. And I have a very good reason to do that. And you can see this from our explicit examples. Just one word, these coefficients delta A, they are fixed by the condition that this lattice derivative operator annihilates our function. So the law is like this. You give me a function that you want to conserve g of f, and I come up with some integers delta, such that if I plug into this equation, this annihilates this function. And the reason why I'm calling this a derivative lattice operator is because in the usual cases that we already know what happens, they correspond precisely to the discrete versions of derivatives. So for example, for constant functions, we have this charge symmetry, and the simplest kind of delta operator that annihilate the function is just the two neighbors difference. So this is just a discrete version of a first order derivative. And these coefficients, delta AR, they should be thought as the coefficients that accompany these functions here in different sets. So in the end, for the charge symmetry, this weird looking expression here simplifies to just a product of two bosons. One at side A plus A, one at side R plus EA with coefficient 1, and another at side R with coefficient -1 that I just put this dagger here. So minus negative signs here, they relate to daggers in our bosonic language. For dipole, we can do the same. So we want to find the simplest lattice operators that annihilate degree 1 polynomials like x or y. And the simplest thing is just a discrete version of a second order derivative. So this is just the function at some site minus 2 times the function at the site in the middle plus the function at the other side, like some kind of weighted average. And as we exponentiate this kind of expression, we can write down our hopping term, our simplest hopping term in our bosonic Hamiltonian, which is just a product of 3 terms. And now you can see that, again, these coefficients that appear here in the function, they're precisely whatever appear here on the top of the bosons. So we have a boson at site on the left, 2 bosons, daggers at the site in the middle, times boson at the site on the right. Yeah. And we can do this for any kind of polynomial. And we can also do this for kind of more exotic functions. So let's say now that I am not interested in considering polynomial functions, but instead something non-polynomial, like an exponential function. So let me fix this integer number m, natural number m, could be anything for now. And I want to impose that my whole system is invariant under this m to the power of x plus y. I'm allowed to do that. No one is going to send me to jail. And this looks weird, very unphysical, but in the end, our bosonic hopping term is very simple. It's just one boson on the left, you destroy one boson on the left, and then you create m bosons on the right. You can argue that this is very weird, doesn't have a straightforward connection with any physical system that you know, but it is possible. I could have that if I wanted. Yes. Sorry? The delta A?
Why are we finding this way? For example, in title, why are we finding that immediate way?
What do you mean?
For title symmetry, delta A equals m plus b minus twice m plus minus where this comes from.
Oh, this thing here? If you, well, this is like the Laplacian operator and without the, so when we define derivatives, we always take like function at some neighboring site minus function at the other site and then divide by the difference of the sites, right? So this is like the second derivative version, yes, precisely.
So I understand for like polynomial symmetries, they would be higher and higher discretized derivatives. But where does delta A for the exponential one come from? The exponential symmetry.
Yeah, so this delta A is never unique. For example, here for the charge symmetry, I came up with this first order derivative, but I could have come up with any higher order derivatives. This is still annihilate this function f. But then this already brings us this idea that if you impose something very, very general, like nth order derivative operator, you also conserve other functions that you are not interested in. So the whole philosophy is always like seek for the simplest possibility. And you can explicitly check if you just take this function and substitute here, this is going to be annihilated. It's a straightforward algebra exercise.
So, but okay, I have another question. So earlier you said that you can't do this for an arbitrary function f. That seems like with this approach you can, I mean, you can discretize, like you can just solve the differential equation for any function. And essentially write down the discretized like the solution of this differential equation.
Yes.
Would be this work.
This would work, yeah, but it has to be consistent with your periodic boundary condition.
I see.
That's the hard part. Yes, and this condition that this delta A coefficient should annihilate this function, you can see from straightforward algebra is that this is intrinsically related to leave this Hamiltonian invariant under U alpha. Yeah, but I don't want to talk about this matter Hamiltonian because you see, this is very complicated. For example, for something that is not as simple as charge, the hopping term, the simplest term is already a three-body term, and you cannot solve this unless you do some numerics or unless you're very, very clever. Instead, I want to gauge this symmetry and study the gauge theory associated to this spatially modulated symmetry, which is surprisingly way simpler. And for doing that, I want to promote my symmetry to be localized. So I want to now allow this alpha parameter to be space dependent. So on every point on lattice, I can have a different alpha number. And I want this to still be my system to be invariant under this kind of transformation. And the price that I have to pay, as usual, is to introduce gauge fields. So introduce gauge fields, A and E, electric fields and their conjugate partners. And they couple minimally with the matter fields. So we can think that now we are modifying the Hamiltonian for something that contains both matter and gauge degrees of freedom. And as we take this B to have this arbitrary site-dependent phase, this A also gets a contribution such that the whole Hamiltonian is invariant. So this is just the generalization of the usual gauging procedure that we have for usual symmetries. You don't look up it.
Which doesn't make a lot of sense because like you are spatially modulating this symmetry, right?
Yes.
And you say, so you must assume this charge operator somehow, like charge density operator somehow, like acts non-locally for this to make any sense, right? If it acts locally, then if you are modulating it, and then you now allow it to vary independently on each side, then it should be the same as just the simple local thing, right?
Yeah, I would say that the action is still local. And the difference between this kind of thing and the thing that we had before is that before we had a global symmetry in the sense that we had this alpha parameter that is just a single parameter for the whole system. So if you fix this alpha label, that is just a label in the U1 group, you fix the symmetry operator.
From this one, like if you let alpha to be arbitrary on each lattice side, right? Then doesn't that just render your F like redundant?
Yeah, precisely. So you should think that I'm just absorbed. So now I want to allow alpha to be arbitrary, but now I'm eating the F inside the alpha. So that's why here in this expression, I don't even have the F anymore. I just have the alpha. So
right, but then you don't have modulation anymore, right?
We do because so the thing is like that. I fix a Hamiltonian. So now the Hamiltonian is fixed. The Hamiltonian is this. And it is invariant under our modulated symmetry. So now I already know these deltas. And now what is the price that I have to pay? Yeah. And the price that I have to pay to introduce this gauge degrees of freedom is to keep the hopping term, the generalized hopping term, and introduce this ace. And the gauge degrees of freedom, they feel the modulation through this delta operator. Make sense?
Another way to think about this is probably something like you are fixing the modulated symmetry as a global symmetry first, and where the gauge fluctuation is a small fluctuation around this.
Could be as well, yeah. Yep.
And that will make the difference then directly thinking about the order one constant global symmetry transformation and doing the gauge fluctuations.
Perfect.
Because
still remembers
the
that.
different order of the gauge field that you introduce through this procedure, and you will see different type of gauge interactions. Kind of a different hierarchy of gauge interactions. You will define the different hierarchy of the polynomial symmetry.
Perfectly. Perfect. But yep. Yes. So now I have this complicated Hamiltonian with even more degrees of freedom. So instead of just the matter, I also have the gauge degrees of freedom. But now I want to simplify this a lot by just integrating out the matter space, the matter degrees of freedom.
I don't have a tiny comment.
Yes.
For this higher order, any order polynomial symmetry, I think many years ago I did some work on this. But the different thing is like I think you guys can consider summation of this different polynomial symmetry.
Yeah, to have something like as a non-polynomial. Yes. Yes.
Because many things you show seems very familiar to what I knew before.
Yeah, perfect. Yeah. So right now I'm just presenting the framework, but then later I'm going to explicitly tell you what the functions we are interested in. Yeah. So just two comments before integrating out the matter. Once we fix the gauge transformations, these immediately tell us what the Gauss law is. So the Gauss law is the generator of gauge transformations, and since the A is shifted by this delta operator, this delta operator also appears here in this generalized divergence rule. And here I'm presenting everything schematically because the details of this delta, like what delta is, actually depends on the function that you're gauging and also on the lattice symmetries that you want to preserve. For example, if you want to preserve full rotation symmetry, as Michael Pratko did a couple of years ago, this delta is like some kind of tensor is like the product of two derivatives, and this lives in some kind of tensor representation of rotation. Yeah, but everything here is just schematically, just to present what's the idea. And we can also cook up the simplest gauge invariant magnetic flux by coming up with this delta hat derivative operator. And the condition over delta hat is such that for any function alpha that we put here, this delta hat annihilates the gradient, this generalized gradient here. And again, the form of this delta hat actually depends on the details of the function and also on the symmetries that you want to preserve. It's not unique. Like arbitrarily is not unique. Yes.
What does this mean? Actually, I'm not sure I understand. The delta hat delta as operators.
Oh, like this? So
you are imposing Gauss law for both the electric sectors and magnetic. Is that all? The delta and delta hat. Or these are not hats.
This is like inverse hat.
So what does this picture like?
Well, so the Gauss law just follows from the gauge transformations. And what I'm saying is that here in our Hamiltonian, if I want to add terms here, I should add terms that are gauge invariant. So the simplest thing that we could add is either something that depends only on the electric field, so like some E squared term. But then if we want to give fluctuations for A, we also, or for the electric field, we also want to add something that depends explicitly on A. So now I'm saying that we want to define this generalized magnetic field. in 2 dimensions. And it's precisely what this expression is. So for example, for the usual symmetries, this Gauss law is just the usual lattice version of
Divergence.
it's just the divergence, yes, sorry. It's just the usual divergence on the lattice. And for the magnetic flux, this would be some kind of rotation.
Which is curl.
It's just curl, yeah, like the lattice version of the curl. And this is gauge invariant because the curl annihilates the gradient.
And then you have a similar expression for
Yes,
all this.
yes.
You have slides for this, or
I do for, yes, for the exponential symmetries I have.
you do it?
Yeah. So in our paper, if you open the archive, we discuss like a lot of examples. But if you fix a function, it's not too hard to guess what this operator should be. Because again, you're always looking for the simplest ones, like the ones that are more relevant in some sense.
But not, you don't put this expression in the slides
For the exponential symmetry, I do.
later.
Later, yes.
Okay.
Yes.
You show.
Yes. We're getting there. Yeah. So now I want to think that we are just integrating out the matter. And this can give us basically 2 possibilities for our gauge theory. So now I have this effective Hamiltonian only for the gauge degrees of freedom. And I have 2 possibilities. Either this gauge theory is on the confined phase, or it's in the deconfined phase. And this actually depends on the parameters that we have here in this ... that I didn't say too much about. But now, just imagine that you have some kind of large term here for your Higgs term, and this kind of breaks your U1 gauge structure down to Zn. And then, so for example, this happens for the usual 2+1 Higgs Maxwell theory. And then in the end, this describes just a Zn lattice gauge theory. So that's the idea here. And this is the phase that we want to study. So that's why I was saying before that we don't care about the whole U1, but just about the Zns. So the price that we pay for this is that now our generators, they are not strictly conserved anymore, but they are conserved only modern. And this is interesting for us because we have this very nice correspondence that the confined phase of gauge theories, they usually are associated to topologically ordered systems. Yes. And now we gauged our symmetry associated to this generator. But this conservation of G is still in our gauge theory. So the gauge theory still remembers of G through its Gauss law and through the magnetic flux. Yes. So
Did you show the confinement and deconfinement here in this slide?
what I'm saying in this slide is just ignore the matter and now focus only on the deconfined phase of this gauge theory. Yeah, so you can think that we are like in the Higgs phase. So the U1 gapless bosons, they just eat like your Goldstone bosons, and then they become massive. They become gapped. And in the end, you broke U1 down to a Zn. And then you have a Zn gauge theory for it. That's what I mean.
Sorry, but in both U1 and Zn, we all consider the U1 gauge theory of your version of the modulated symmetry and Zn version of the modulated symmetry gauge theory. Is it here we're talking about this gauge version of the modulated symmetry?
Yes,
And
exactly.
do you have a combined and decombined phase for both U1 and Zn?
We have a deconfined and confined phase for the U1. So the confined phase is not too interesting for us. And it's probably, if you try to solve the theory for the gapless phase, you're going to find that it's actually confined exactly because of the proliferation of instantons. We are actually interested in deconfined phase. And what I'm saying is that one way to access this phase is through Higgs mechanism. So you know this duality between the Higgs phase of a Maxwell theory to a double Chern-Simons theory in 2+1. This is precisely the same idea. So you go to the Higgs phase, and now this is secretly topologically ordered and described by this topological action. Make sense?
And you will call this deconfined.
And I call this deconfined phases.
Yeah, but access from the U1 is from
I would say that this deconfined from the U1 phase.
also from deconfined U1.
That's
And
what I would
takes
say.
down to deconfined Zn.
Yes.
That's okay.
You don't agree? Well, maybe we can discuss further this.
Yeah.
But actually, you don't have to care at all about these names,
Yeah, this
because the whole thing that I want to say is that now the bosons, they are not strictly conserved, but only mod n. And it's very convenient to write everything in terms of these generalized Pauli matrices, X and Z's. So, sorry. So people call these Higgs mapping. They are usually associated with this Higgs phase. And it's very convenient because now instead of dealing with these weird operators, the bosons and the gauge fields, you can think only of this n by n matrices that obey this clock algebra. That's how they call it. So they call the Z operators clock operators and the X operators are shift. And if you fix a basis where Z is diagonal, the action, what this algebra tells us is that the action of X over this state is just to introduce one unit of this 2 pi over n flux. I don't know the Heisenberg group.
So it's a central extension of Cn plus Cn. So each of these X and Z, they generate a Cn, but amongst each other, they almost really have to.
Perfect. Yes. So yeah. So Z to the power of n is just the identity operator. X to the power of n is just the identity operator, but they have this mixing between them. Yeah. People say that.
Okay.
Yes.
Sorry, I still didn't know this group. What's the physics here for this group? What do we mention? What do you want to mention this group?
Which group? The Zn group or the Heisen? Oh, I don't know. He just asked it. This is the same
It
thing.
was a math question. It was not.
What's the physics important?
Yeah. No, don't think about the Heisenberg group. Just think of this very simple operators and they obey this algebra, and I will push the boundaries here and call this Zn kind of Pauli matrices. That's what I'm saying. Yeah. And the cool thing about that, why we want to say all of this, right? It's just because now that we have our Gauss law and we have our magnetic flux that we defined before from the delta and the inverse hat delta operators, we can define some kind of toric code like Hamiltonian for this system. And what I'm saying, so when we do this, we stop to think of our theory as a Zn gauge theory, that all the states should be constrained to be gauge invariant, but instead we impose the Gauss law energetically. And then we think that the ground state or the low energy states, they do not violate the Gauss law, and this gives us this notion of what a E excitation is. So in the end, I discussed all of this just to get to this kind of toric code like Hamiltonians. So you can think that this is something like a star term. This is like a plaquette term. And this is cool because all these terms, they commute with these terms from construction. Yeah. So when I was saying that break U1 down to Zn, Higgs mechanism, blah, 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 all that I wanted to really say is just now I can effectively incorporate all the physics of the Zn phase in this kind of toric code like Hamiltonian. Yeah, where these Q operators and these B operators, they are just the exponential of charge and the flux that we had before. So they are completely defined in terms of these Z's and the X, in terms of the delta A's coefficients that I mentioned before.
What's the exponent of delta mid there and delta inverse hat?
This
Yes.
is there in the same sense that we had before with the bosons. These are just like coefficients of our derivative operator. Yep. So every time that I say the deconfined phase of the spatially modulated gauge theory, you should have in the back of your mind this Hamiltonian. just like the toric code, usually it incorporates all the physics of the ZN lattice gauge theory.
But you also use this delta as some operators, right? But here you express this delta as the coefficient, and there's some.
So the relation between them is this. So the coefficients, so this is the thing that is appearing in the Hamiltonian. These are integer numbers.
So you are taking that coefficient from one of the older exponential.
Exactly. Yeah. Yep. So the coefficients that we have there are precisely the coefficients that we have here on the top of the bosonic operators. Yes. So this is the story. You give me a function, I follow all these procedures on the slides, and then in the end I hand you all this exactly solvable Hamiltonian. So in this sense, this kind of framework gives us this very nice story of how we can study exactly the low energy physics of any gauge of the deconfined phase of any modulated gauge theory. Yeah, so from construction, because of this imposition that the inverse hat delta annihilates delta for any function, these two operators commute, which is just a lattice statement that the flux are gauge invariant, because Q here are precisely the generators of the gauge transformation. Yeah, and now we can just solve the system. So it's very, very nice. We don't need numerical methods. We don't need perturbation theory. We don't need anything. We can just diagonalize, find a basis where all the operators in the Hamiltonian are diagonal. And we can just find the ground state by finding the state where all the BRs and the QRs have eigenvalue +1. Simple like that. The system is gapped, as very often is the case for this kind of commuting projector Hamiltonians. And violations of this eigenvalue +1, so B and Qs, they usually have eigenvalues exponential to the 2 pi over n, any integer of those, an integer combination of those. And anything that is not +1, we interpret those as excitations. So the excitations, they are localized in space, just like in the toric code Hamiltonian, and they correspond to these eigenvalues that are different from.
By the way, the equation that you use, this delta inverse hat delta is 0, is more or less using the condition of a d squared.
Yeah, this is like a lattice version of this.
But this may not be true sometimes when you have a localized defects at a core.
Yes.
So I suppose you won't be approaching somewhere with some defects, right? The theory discussed with this mention.
I would say that these are like the lattice versions of d squared. And here, since we are always on the lattice and we are always talking about discrete valued functions, we don't have like this kind of breaking down out of smoothness. I would say that this is just what is this? This is just a property of coefficients. These delta here, they are defined by the equation that I showed before, and they are just a property between numbers. Yeah, so these are just integer numbers. We fix this, these f's, they assume values over Zn. And I would say that property holds always.
I mean, you know what I mean, like.
No, I know precisely what you mean, yeah.
Divergence of curl A, you will say these are 0.
Yeah.
Magnetic multiple.
Yes, but there you have some kind of a smoothness condition, right? And when you have these defects, then your smoothness is kind of, you don't have a smooth configuration, and then you can have this kind of d squared not equals to 0. But I think, at least here in the lattice, we don't have this kind of problem. But I know precisely what you mean.
Yeah, but there's an interesting question here. It's like, suppose you are able to classify some kind of quantum number for this d square, which is delta inverse hat delta in the lattice system. Then you might define some version of the trend number, right? Because the magnetic multiple is the case divergence of curl A, which is integral of the surface will be the flux B.
To be quantized.
But that's quantizing.
Yeah.
Which is the first trend number.
Yes.
Yes. Which is the magnetic multiple quantized charge.
Perfect.
Like if there's something like that for those theory, then you can classify some quantum number, which maybe beyond two numbers or something.
Could be, I
Yeah.
don't know,
And-
spatially modulated Chern numbers
That's
associated.
something to see directly.
It is indeed, yeah, we should talk more later about this. It is interesting that. Yes,
I have something to but I don't understand, but like, so basically you're saying you're having something like these B's and Q's at different positions, they commute with each other, right? So everything is conserved, and then you have infinite of them. And of course, then your ground state degeneracy will scale with the system size.
so you have. So the ground state degeneracy is going to come from constraints among these Qs. So you should think that we have as many Qs and many Bs
Oh, but
as degrees of freedom.
they have to take that one.
Uh,
Okay, so forget about the ground state degeneracy, but I'm trying to, so you say all these excitations are not going to move, right? And that's,
oh, it depends, it depends. It depends. So it depends on the function. So are you familiarized with the usual toric code that Kitaev,
that's sometimes.
right? So there, when you create two excitations, they are always constrained to be created in pairs. And after you create them, you can just move them around.
Okay.
How restricted their mobility is actually depends on the function that you start with. Yes.
And how do I see it from here?
Oh, we cannot see it from here, not yet. Yeah, there is a constraint over the values of over these eigenvalues here. The eigenvalues of Q and B's, when we put them on a periodic lattice, they cannot be anything. They're constrained. And the constraint is precisely these equations here. So when I say that the gauge theory remembers the spatial, the generator G of F that we started with is through these equations. So the conservation laws and the matter theory becomes constraints on the gauge theory when we put these periodic boundary conditions. So you don't have to worry where these expressions came from. You can just believe me that they are true. But the idea is the following. If you have an excitation sitting at some site R, so the eigenvalue of this Q is not 1. In order for this to be identity, you have to have some other excitations or some other group of excitations sitting somewhere else. And you have this very fine-tuned balance between the charge of the excitation and the function and the position that is sitting. So that's where this constrained mobility comes from. And it's also, so these constraints, they ensure us that the ground state degeneracy is going to be non-trivial. So every time that I have this constraint, we can do a very basic, very not hard calculation and find what the ground state degeneracy is. We don't have to bother about that, but that's where it comes from. And it also ensures us that the excitations, they should have constrained mobility. So that's the intuition. Yeah, and these F tildes here that I'm talking about, they could correspond to emergent or not emergent symmetry functions, spatially modulated symmetries, but instead of the charge, we have the magnetic flux. I'm going to discuss later what happens for our specific case, but I say that I lied to Juven, and this is not going to be 1 hour. Yeah, but the idea is that we can use this whole procedure to study exactly solvable realizations of this sum of gauge theories. So instead of imposing just one function, I could impose n functions and just find out what my Hamiltonian is and just study everything. Yeah, so very quickly, the models that we already know and love in the literature, they fit very nicely in this framework. So for example, this ZN toric code is just the gauge theory associated to the low energy physics of the ZN toric code. Is the low energy physics associated to the gauging of global charge. And more recently, we had in the literature this thing that people call rank 2 toric code. That is just the deconfined phase of the gauge theory associated to the charge plus X dipole plus Y dipole. And then you can solve for the Hamiltonian and you can find that they match precisely the lattice models that these guys have. And so on and so forth. Like in our paper, we go in a lot of details, how many models we can recover, but that's not so important. But now the part that Juven was interested about which is that subsystem symmetries, they can be thought of as specific cases of modulated symmetries. And if you never saw subsystem symmetry before, then the only thing that you should know about it is that the generator of the subsystem symmetries, they are sums over some kind of charge density, not on the whole system, but only on a subsystem, only on some submanifold or some sublattice. So here, lambda is the whole lattice, omega is some kind of sublattice. And this very trivial way of writing this sum with this delta allow us to interpret this as a modulated symmetry. So now you're saying that the subsystem symmetry actually is a modulated symmetry that acts very sharply, that give us 1 when R belongs to the omega and 0 when it doesn't. And now we see that usual 3-dimensional fractons, they're associated to an extensive number of subsystem symmetries. They come from the gauging of this extensive number of modulated generators. So imagine that we fix a lot of submanifolds, let's say a lot of planes in our 3-dimensional system. And we just fix this function, the function inside the G, to be a delta function. So this n here is of the order L, and it's precisely this kind of condition that gives us the ground state degeneracy that grows with the system size in 3D. If we try to do this in 2D, so let's say that we have a square lattice, and then we say that each line of our square lattice is like some subsystem, some lattice that we want to conserve this generator here. In the end, when you do all this procedure, what you get is not a topologically ordered phase. So that's why the straightforward mechanism doesn't apply in 2D. And that's one of the motivations as well to corroborate with the conjecture that we cannot have fractons in 2D. So now it leads to the question, what can we do if we just require order 1 symmetry generators? Like we don't impose an extensive number of conserved quantities, but just, I don't know, 2 or 3 or 4 of them.
Actually, I can't get those. What do you summarize in colloquial way of looking at it? So you
so this whole slide is just a parenthesis. This whole slide is just a parenthesis in my talk, just saying that subsystem symmetry, they fit in this whole framework that I mentioned before through this very trivial identity. Okay.
On the previous slide, you also show separate example. Those examples are also subsystem symmetries.
Those examples are not subsystem symmetry. So these examples, they are just charge symmetry and charge plus dipole symmetry. So these are not subsystem symmetries.
So how about those SQ model kind of things? They are subsystem. Give you subsystem.
Yes.
So just make sure how
so there is an equivalence between them in some cases. So for example, if you consider the rank 2 gapless gauge theories that Practical taught us, if you Higgs it down to Zn, sometimes you can recover a Fracton system like the X cube, and sometimes you just recover some copies of 3D Tori code. And the difference between what happens in each case is that whenever you have fractons, you have this kind of subsystem symmetry. And what subsystem symmetry here means is precisely this. We have the conservation of charge along different submanifolds. So for the X cube, along each plane on the 3-dimensional lattice, we have that charge is conserved. Yes. So subsystem symmetries and modulated symmetries, they're kind of thought as different, but in the end, they're all the same.
But just using the previous slide, so the example for SQ model, how do you map to the symmetry? Can it be written as G of something?
Well, I would say that the X cube model is a sum over a lot of G's. So we have order L G's. So yeah. So this is I mean by not order 1, but order L G's. And the arguments for each one of the functions are like deltas. So you have a delta, a Kronecker delta for the first plane, a Kronecker delta for the second plane, for the third, and so on and so forth, for all the planes.
And the Plako's example you want, you probably just answer, but I didn't get the info.
So the thing that I
Yeah.
would say for practical
Yes.
is associated to this actually.
That one.
But in some cases where you couple with matter, these actually give us the emergence of these subsistence symmetries.
Okay,
Yes.
sure.
Yep.
Okay.
Okay, how much time do I have?
Keep going 10 minutes.
Okay, I can wrap up in 10 minutes. Yeah. So now the rest of so this is the whole framework. And now the rest of the talk, that is not going to take too long, is to answer this question. So if we cannot have the gauging of an extensively large number of generators in 2D, what can we do in 2D? So we can start by just doing something very simple. We can start by studying the gauge modulated theories, the modulated gauge theories associated with G of polynomials. When we just put F's to be polynomials, and we can check whatever happens. So what happens is this. When Michael Pretko did the whole thing for U1, you show that gapless excitations, you find a gapless theory, and any excitation actually have their mobility restricted. So this is for the U1 case. When you Higgs U1 down to Zn, something that you don't want to happen actually happens. You have now this emergent order n length strings that can move excitations around. So this is just a property of the groups and how the Hamiltonian is written. But this is something that you don't have in the U1. So now the price of having a gapped phase, so when you break U1 down to Zn, we have a gapped phase. So the price of having a gapped phase is actually to move excitations around. So if you try to gauge polynomial symmetries, so this is the case for dipolar, so just degree 1 polynomial in X and degree 1 polynomial in Y. But in general, if you try to do anything that is polynomial, you're going to have something like this. Apparently, it's something that is not possible to escape. And that's why this rank 2 Tory code that you mentioned before, this is actually not a fracton. Yeah, so Han and collaborators, and also this paper from Sal and Chao-Gang, they discuss how the particles now can move when you break U1 down to Zn. So I went very quickly through the slides, but you don't have to worry a lot. The only take-home lesson is that dipolar or polynomial symmetries in general, they are not good enough to give us Fracton physics in 2D. So now this is the main motivation for us to do something very drastic and do something that is not a polynomial. So we don't introduce. These people introduced and we copied these ideas of exponential symmetries. So we go to our generators, and here our function, we impose this to be some kind of some exponential dependence on the function. So G is any polynomial, and now we want to impose that a to the power of G is conserved. And we want a Hamiltonian that conserves this. As Juven pointed out, in the end, if you Taylor expand the exponential function, what we are saying is that we want to conserve this very fine-tuned, delicate balance of different order multiple momenta. So we have this coefficient alpha 0, and then we conserved for G of charge, plus alpha 1 for G of dipole, and so on and so forth. So already intuitively, this gives us a very constrained dynamics in the low energy. And now for concreteness, this is the model that we're going to study. This is the model that we spend a lot of time in our paper discussing. And it's just the deconfined phase of the gauge theory associated to this sample. So in the end, when we do the whole procedure, we find this Tory code like Hamiltonian, and the interaction terms, the star terms and the plaquette terms, they are given by these expressions. So this is the explicit expression for the derivatives that you asked before, Juven. So the delta A's, they are just these coefficients here, -1, A plus 1, -1. And for the inverse hat delta, they are just A plus 1, 1. So you can check that these actually annihilate all these functions, the 4 functions. And this delta hat actually has the property that annihilates delta, and this is exactly solvable modeling. So all these terms, they commute with all these terms. So again, you can argue that this is very unphysical Hamiltonian, very weird. But this is more like a matter of principle. What is possible, right? And now I just want to flash through the properties. If we just start with that Hamiltonian, what does it buy us? So first, we have some consistency condition that relates what the A number, so this A here is an integer number, mod n, and what it has to be in relation to n for this to make sense. And A cannot be 0 mod greater than. We don't have to worry too much what it means, and where this comes from. But you can already see that these very number theoretical properties emerge in this kind of systems. We can also compute the ground state degeneracy, and this is what it gives. This is what it looks like. So it looks very ugly. It looks terrible. And as you can see, this is in 2 dimensions. This depends explicitly on the system size, Lx and Ly. But this does not violate the theorem that I mentioned before, because the GCD is always upper bounded by the smallest of its argument. So if this A to the power of L is, I don't know, 10 to the power of 23, but this NA here is just 4, this is going to be like order 4. So that's how we can have UV error mixing, but does not violate the bound, which is good. So you're not violating any mathematical theory. And this NA here is just this N divided by the GCD. So again, all these number theoretical properties, they come to haunt us. Yes, so this is the upper bound for this ground state degeneracy. Yep. So that's what I meant before by order 1 in L. Yeah, so now just to finish, and then we can enjoy Thanksgiving break. We can explicitly see how the excitations can move through the strings operators. So now the whole system is exactly solvable. We can find what these string operators look like. So they are the analogues of the toric code string operator that creates anyons. And to obey those constraints, to conserve all those quantities, they have to create excitations in a very specific pattern. So we have basically 3 types of string operators. The first 2, A and B here, they create this bound state. So this is just a dipole, like -1A, 1 minus A, and -1, 1, A to the power of S, and minus A to the power of S, where S is just the size of the string. They are not interesting for us because they move bound states. They do not move a single excitations. But the string that we are actually interested in is this more exotic string, defined as x to the power of these alpha I functions. And these alpha i's, they are given by this sum from 0 all the way to the I of A to the power of G. And this function is defined only model. So again, very weird looking expression for a string operator, but it does what we want. In one of the endpoints, it creates a -1 excitation, and in the other one, it creates a bound state of a charge alpha S and 1 minus alpha S, where again, S depends on the system size. So this is going to tell us when this model behaves like a fractal. When alpha has some integer solution that is 1 mod n, then this third excitation go back to the vacuum, and this effectively moves this -1 to here, to this point here. So this is the case where the model is not a fractal. We are, however, interested in the case where this equation has no integer solution. And when does that happen? That happens every time that A is co-prime to NA. where remember, an A is just the ratio of A divided by the GCD of N with A. So when this happens, we are claiming that we have this type 1 Fracton physics. So just now to wrap up, I know that all of you are tired because I'm tired as well. I'm going to skip this. This is the summary that we get from studying these models.
Maybe you don't skip that.
We don't skip that?
Yeah.
Okay, Juven told me to not skip that. We can formalize this idea of how particles cannot move using this tunneling time. So we had before our exactly solvable Hamiltonian, that is, I'm just calling h of x exponential. And then now we perturb it with some external field, g, where g is very, very much small in comparison to the gap. We can show, we do this in the paper, in perturbation theory, that if we have one excitation sitting on the center of this radius r region alone by itself, it's going to take a time of the order g to the power of minus r for this excitation to leave this area. So we can show this in perturbation theory, but this is like a huge time. So if we have a single excitation sitting on our system, this is never leaving the system. That's what it means. And this is almost as good as their three-dimensional cousins. So for the three-dimensional fractonic systems, they grow with the minus r to the power of squared. And the intuition is that here, the operators that move excitations are membranes. So that's where we have this r squared. And the excitations that move r, and here in our model, the excitations are moved by strings. So that's why I have r. Okay, so now the summary of the properties. In this exponential gauge theory, these are the things that we find. We find that the system is topologically ordered, check. We find immobile particles that cannot move at all, check. And we have an explicit UVIR mix, like the weird ground state degeneracy looking expression. We don't have, however, the subextensive ground state degeneracy growth, which is good because this would violate a Haas theorem. So some of us would be wrong, and it would be probably me. And we also don't have membrane operators. And this is a table comparing different models that we see in the literature. So as you can see, as we go down on the table, we are gauging more and more exotic kind of symmetry, modulated symmetries. And then these bias these fractonic behaviors. So for the Terry code and for the 2D rank 2 Terry code, we don't have immobile particles. But then for the two here in the two last rows, we do. And we can see that these two cases are also special because of this tunneling time that grows exponentially with the region that the particle is isolated, and the same for the 3D fractal. So just to finish, I always like this picture very much. Just to catch up, we show that these modulated symmetries, in the end, they map the problem of classifying and characterizing quantum phases into studying properties of functions, which is very nice. Like we study functions for a lot of time now, so I know a lot about them. And although polynomial symmetries, they cannot restrict particles from moving, exponential ones can. And the take-home thing that we should take in our heart today is just as you choose more exotic functions to gauge the g of the function, this kind of walks you through this spectrum of quantum phases. So it's not like we have topological order in one bucket and we have fractons in another bucket. It's almost like as we gauge stuff that are very, very weird, we walk through this continuum of different phases that show us how rich nature can be. Yes, that's it. Thank you. Yeah, thank you for inviting me, and thank you for all the questions.
Any questions, comment from audience?
So what on the previous slide, what did you by membrane operator?
So in usual three-dimensional fractals, like in the X-cube model, for example, the way that you move the excitations around is through this extended two-dimensional operator. So you like apply sigma z operators along the whole bulk of this membrane, and then you create excitations at the corners. But here, the way that we move excitations are not through membranes, but through strings.
Is there any non-local operator that can move this fractonic excitation?
No.
So the only way to move it is to annihilate the string back and then create a string somewhere else.
Exactly.
Is that spectrum continuous?
I don't know. Yeah, I said it was continuous, but in the end, I think we have as many points as we have functions, different integer lattice functions. Yeah, it's just like abusing notation here to say that this is continuous.
Even given a function, like there isn't a unique solution to that, like corresponding to like this delta A stuff.
There is not, yes, that's correct.
More like in terms of this delta solution, like, if there is a function that.
Yeah, I think you're right. Like the deltas characterize the thing, yes. Yeah. But in the cases that we found, we always have this possibility, like when you have two deltas that are equally simple, one of them always allowed for like extra symmetries that you don't want. And then you just get rid of this. But I think if you allow for complicated enough deltas, then they should compete.
There's one question from Aaron Worker.
Oh yes, Taron, when do you?
Yeah, thanks for very nice talk. Can you hear me?
Oh yes.
Great. Yeah, I have maybe a couple very basic questions. I'm a bit confused. Just to understand your main message, is a claim that this 2D exponential symmetry leads to completely new topologically ordered spaces which are stable to any perturbations in 2 dimensions. Because 2 dimensions, generally, we don't know many things beyond, for example, just the standard, let's say, gauge theories or Chern-Simons theory, which are gap phases of matter. But here, the main result is that you have now phases of matter which are completely different than any known gapped topological phase. And so if I add any generic perturbation to your Hamiltonian, which like any term, it will retain the properties you mentioned. For example, the ground state degeneracy you mentioned is robust to any arbitrary perturbation. Is that
yes? So all these properties that we found, like the mobility of the excitations and the ground state degeneracy, they are all robust against arbitrary perturbations. But I'm not sure. Well, I don't know if this is like new. This is a new phase of matter, or if this is just like it gets in the different buckets, because depending on what you call Fracton systems, you could say that this is just a Fracton in 2D. So in this sense, it could be something new. But if you say, for example, that for Fracton physics, you need membrane operators and you do not allow string operators at all, or you want, I don't know, some sub-extensive ground state degeneracy growth, I would say that this is not a Fracton then in your definition. And this is just some kind of weird UVIR mixing topological order. So that's why here in the end, I put this kind of spectrum, this continuous spectrum, that maybe our classifications of phases of matter, they are too naive, but maybe we don't have two buckets, just like they are either quantum spin liquids or fractons, but maybe we have this whole things in the middle that we don't agree what we call those.
And how does one think about anyons is there some notion of thinking about braiding and those kind of things in your phase? And for example, at least for standard phases of matter in 2D, there is a one-to-one correspondence between number of ground states and number of distinct anion types generally, right? Is there such a thing here, or?
So the ground state degeneracy that we found here in equation 26, this is counting basically the number of anyons that we can create, go around the system and annihilate again.
Right. So it's similar to.
Yeah, so you can think that these things here, they are actually counting how many lineons we have. So we create lineons and like as these bound states, we move them around the system and then we annihilate them. If we consider just a single particle, like a single anion, using this U operator here that I mentioned before in equation 30, you cannot move it around the system and then annihilate it again.
I see.
So in this sense, this guy is not there.
I see. Maybe one very last question. If you so the partition function of this does not have any singularity at finite temperature. Is that true?
Sorry, say that again.
If I study the partition function of this as a function of temperature, is it true it has no phase transition? It is smoothly connected at any non-zero temperature to infinite temperature?
Yeah. It is. And this is exactly related to the non-existence of membrane operators. So since we have these lines here, if you turn some small temperature, now we have non-zero density, and then everything is doomed. Yes, very good question.
Yeah, thanks so much. Very, very interesting.
This fractals, they are not anyon.
They are anyons.
They are anyon.
Yes. Yes.
Oh, I see, but
We can also compute their mutual statistics.
That's like. So summary is, so when you say it's neither pure homological or there no Fracton, do you mean just mixing between them, or do you mean something else between the mixing?
Something like that has some properties of topological order and some properties of fractals. Yeah.
So there will be mixing between the two.
Like some mixing fixtures, yes.
But you're not excluding, you're not saying that there is something even beyond either of the problems.
No, it could be. Yeah.
You will find example.
Sorry, say that again.
I said that because this statement can also mean that perhaps there is something beyond topological order and beyond fractal and beyond mixing. But you're not implying that.
I'm not implying that is something beyond, yes.
I'm just mixing between.
Yeah, that's how I see. But I could be wrong.
Thanks.
Yep. Thank you very much.
You. Any other comments questions last time? Okay. If not, thank you very much for coming to the Quantum Math and Math Physics Seminar Series. Thank you. Thanks again. Happy day.
Thank you very much. Thank you for inviting me. And thank you all for the very nice questions. I can stop sharing.